So hopefully you've mastered the idea of balanced chemical equations and this first pattern of double displacement. Before we get into the next driving force of chemical equations or chemical reactions, we're going to talk a little bit about different kinds of equations that you can actually represent reactions with. So 3 different types of chemical equations. To this point, what we have been writing are molecular equations. These are the regular ones. And so this is the kind of thing that you've been doing up to this point. Another kind of way of representing a chemical reaction would be with a complete ionic equation, and so or sometimes total ionic equation. Basically what this says is that anything up here that is aqueous, we are going to show as its composite ions. You just show how it would be actually floating around in that beaker because it's an aqueous solution. So the barium nitrate also blown apart into its ions. And these, if you take a look, there's some rules here. So subscripts of ions become the coefficients. And so what we're saying here is that 2 down below for the potassium means that we have 2 potassium ions in solution. Coefficients stay coefficients. And so over here we have the example of 2 in front of our potassium nitrate. So they stayed out in front. And then ions that are both reactants and products are called spectator ions. And so that's kind of key in going to the third kind of chemical equation. We'll get lots of chance to practice these, so I'll keep going. If you were to take a look and reduce anything, cross anything out that was a spectator ion, it's floating around before and it's floating around after, what you're left with then is just the net ionic equation. Now, these are the things that are actually involved in the chemical reaction. We know that the precipitate or the formation of a solid is that driving force. And so this is really the nugget of chemistry that is causing that chemical reaction. And that would be called a net ionic equation. So you're probably familiar with the molecular equations. Blowing everything that's aqueous apart into its ions is the complete ionic equation, and crossing out those spectator ions is how you get to the net ionic equation. So these ones take a lot of space. I'll try and mimic this. I always seem to run out of paper. So we're going to go from these reactants and write out the molecular equation, the full or the complete ionic equation, and then reduce that down to the net ionic equation. So we've got aqueous sodium sulfide, so NaS. When I take a look at the combining capacities, my anion sulfur is a 2 minus, so Na2S. And I know that that's aqueous. These are solutions we're mixing together, is mixed with aqueous copper 2 nitrate. So copper 2 and nitrate. We're going to practice the double displacement pattern to complete our molecular equation. So sodium and nitrate are going to bond together. I'll take a look at my solubilities chart to determine the state of that. And then copper 2 ion is going to mix with, or bond with, I should say, the sulfur anion. If I take a look at the combining capacities here, I should be fine on the formulas. You should take a look at balancing this when I want to fill in those brackets so bad I kind of forget sometimes. So if I were to balance metals, polyatomics that stay together, and everything else, it works out like that. To fill in these brackets here, I consult my solubilities chart. When I do so, I'd figure out that my sodium nitrate is aqueous and my copper 2 sulfide, is my precipitate. And so it would be solid. The complete ionic equation, everything that's in here that is aqueous, I'm going to show dissociated into its components, right? Dissociated into the ions that make it up. I'd have 2 sodium ions in solution. Do you notice I started really far on this side of the page? And I'd have a sulfur ion in solution. I'd have my copper 2 ion in solution. I'd have 2 nitrate polyatomic or anions in solution. I'm going to have 2 sodiums as a product in solution, and 2 nitrates in solution. Been doing so much of the aqueuses and blowing them apart into their component ions. The last one is a solid, and so it doesn't dissolve and it doesn't dissociate. So I would simply leave it like that. That is your molecular equation and your complete or full ionic equation. The next thing that we do to get to the net ionic equation is that anything that is the same, anything that's just hanging around watching things happen, are my spectator ions, and I can cross them out. And what I do is write what's left behind, because that's how I form my net ionic equation. And so writing this out, everything that's left behind gives me my net ionic equation, really capturing the driving force behind this chemical reaction. The last one I'll write out, and I'll do without talking. You can check your understanding. 4s always become 9s on me. Practicing the double displacement reaction. Oh, I did them in opposite order this time. So that would be my molecular equation. And then taking it to the next step, the full ionic or complete ionic equation, everything that is aqueous, is going to come apart into its ions. Coefficients stay as coefficients. And subscripts become coefficients, like in the case of this 2 nitrate. This is the thing to not get tripped up on. When it's solid, it just stays together. It doesn't dissolve, so it can't dissociate. It's insoluble. And look at me, totally running out of space. I always try and plan ahead. So there's my very complete ionic equation, and then I'll switch colors just so it doesn't distract too much. Anything that's hanging around before and after are my spectator ions. Sometimes, to be honest, I forget to balance as I go, and usually it's at this point where I'm like, wait a minute, something is wrong. It doesn't balance out. So if you balance it off the top, you should be fine. And sometimes it gives you a check before you kind of complete your work here. So everything that's left behind is your net ionic equation, really illustrating that driving force of the chemical reaction.